Hmm. This is O of. Is this O of n squared? I think it is. Because what if you have like 8, 9, something like this? Or no. And then, yeah, like as long as all of this is ascending. As long as all of that's ascending, you have O of n squared, I think. Space complexity. Auxiliary is O of 1, but... Oh no, it's overall O of 1. We can create any extra space. Yeah, O of n squared. Monotonic stack. This is faster? It is. let's see. I didn't look at the solution. Make a stack. Oh, you can do like it's like yeah, something like this. I see. Yeah. This is very similar to another. Oh, that's interesting. Space complexity is. Yeah, it must be the space complexity that messes it up. This is very similar to another Leetcode question. Nice. I'm gonna get water. I'm tired. Alright. I've been slacking a little bit, so. I'm going to try to finish. I haven't done the Leetcode in forever, so I'm going to try to get through it as quickly as possible. And hopefully not mess up. So this one we use a hash set, we add, and then if we cannot add into the hash set, then we iterate through everything and return true. I should get used to explaining my process. So here we make a frequency array, and well, first we can check if S and T are the same length. If they're not, then they're never anagrams. And then we can make a frequency array that is 26, that has a length of 26. And every time we encounter a letter in S, we increment, and every time we encounter a letter in T, we decrement. And then we go through the entire frequency array, and then if anything is not 0, then, or if anything is greater than 0, then it is not an anagram. it's important too because this is technically O of 1 because frequency length is always 26. So technically it's a constant. But this is n because as the length of s increases, the time the time the problem takes to complete will also increase. And then this is technically constant space too. Yeah, that's what I thought. Okay, two sum. So here what we'll do is, well, the naive approach, I should get used to saying the naive approach too. The naive approach is to iterate each number like so, and then for each number, we iterate every other number and check if we get the target. The problem with that is the time complexity is quite intensive. It's O of n squared. So what we can do is we can iterate through each number, cache the values and their indexes, and as we iterate through each, we can check if its complement exists in the cache. And if it does, then we can just return that, and that will decrease our time complexity to O of n. But it will increase our space complexity to O of n as well, from O of 1. So we can do like something like this. And then this is just a false, but we'll never hit this line because I think there's guaranteed, yeah, only valid answers exist. This is O of n space, O of n time complexity. Wait. Group anagrams. Okay, so this is similar to the anagram. We just add on to it. So basically, we iterate through each word. We create the frequency array, and then we stringify that. We turn the frequency array into a string and use it as a key to a hash map that stores a list of the words, the anagrams. And we can use the frequency array as the key, and it'll store the list of all the words under that key. And then we just create and then we have all of them in a hash map. We have the anagrams grouped in a hash map at that point, and then we can transform it into this output variable type. So here, it'll be string actually, and then it'll be a list string. And then we'll iterate through all the strings. And then we will create a new frequency array with the size of 26 because there are 26 letters in the alphabet. And then we will iterate through each individual string, and then we'll take each character's position or character's lexicographical value relative to A, and then create the frequency array, and then we can make a key by saying arrays.toString and then throw the frequency array in there. And then if the map does not contain the key, then we put an entry in for the key and a new array list of strings. And we get the key, and then we add the current word in it. think that works. Maybe it's implicit. I know there's a way to... Is this? Yeah, there we go. Probably because it doesn't know which part of the collections. Yeah, you can't. Okay, space complexity is O of n here, and the time complexity is O of n times m, where n is the number of strings in the array and m is the average length of the strings in the array. Oh, this is a closed off one, I think. Yeah. So here, what we will do is we can iterate through each of the... To encode, we iterate through each of the words in this list, and we add... we use a string builder to take each individual word, add the length of each word, and then add the length of each word to the string builder, add a break, like a pound symbol, to indicate that the length is complete, because we don't know how many digits the length of the word is. It could be like 100. And then the word, and then we keep on repeating that. So it'll be length, breaker, and then word, and we add that to the string, and then we return the string builder as just a whole string. And then to decode, we use a two-pointer method where we take one index and then iterate, or we take one index and then the second index, and then we iterate until we reach the breaker, and then we use that to identify how long the word is. And then after the breaker, we will take that portion of the string and then add it to the list, and we'll keep on doing that. So we'll identify the length, use the breaker to identify the length, and then we'll take that length from the breaker onwards and then add it to the list. So here we'll declare and initialize a string builder object, and then we'll iterate through all the strings. And then we'll take the string builder and append the length, and then we'll append the breaker symbol, which is, let's use the pound symbol, and then we'll append the actual word itself. And we do that to each word in the list. And we'll return the string builder.toString, so a string version of that. Here we take one pointer, and we say while I is less than the length of the string, and then we have a second pointer here that equals I, and then while the current character at j does not equal the breaker, we'll increment j, and then we'll get the length by saying string.value of str.substring between the beginning and the end. And we can do this while it's on pound here, because substring is exclusive at the end. And then we'll increment j1, no. Will we? Yeah, we'll increment j1. Or no, we can say just like I equals j. Actually, we'll increment j once. And then we will say we need the output list. So we'll make string so something like this. And then we say output.add j, string dot substring j, and j plus length. And then I equals j plus length. And then we will return the output string. What's wrong? I think that works. Yeah. So here, let's see. Length. These we can denominate to constants. So this is O of n, this is O of m. So this, the encode method, its time complexity will be O of n times m, where n is the number of strings and m is the average length of the strings, and then the space complexity is O of n times m as well. But that's technically like O of n, because it's just the amount of characters in this list. But yeah, n times m. It's different when it's like not the same as it's not necessarily the same as a quadratic time complexity. And then decode, we have a space complexity of O of n right here, and then time complexity of O of n with this, because it's just a 2-pointer, so it's just 2n here. So yeah, there we go. I forgot what this album is called. Is this called Cadenes? I don't think this is Cadenes. Yeah, I don't think this is Cadenes' algorithm. So what we can do here, it doesn't allow you to use the division operation. Otherwise, you'd be able to multiply. We'll find the product of the entire array and then just divide by each individual element. So what you can do is you can store, for each value, you'll store everything to the product of everything to the left of it and the product of everything to the right of it. So like in this case of 2, we have the product 1, and then we have 3 times 4, which will be 12. So it's 1 times 12, which will get us our answer. Here, it's nothing here, but it's also 2 times 3 times 4, which is 24 here. And then same here. It'll be 2 times 4, which is 8. And then this is the same thing. So if you store the product of everything to the left of a certain element and the right of a certain element, and then multiply it against each other through the cumulative property, you'll be able to get the answer for this. So yeah. Here I can make an array called output that has the number of lengths. So we have the length, we have an output array, which is the same length as the input array, and then I started the loop at 1 because there's nothing to the left of the first element. So what we can do is we'll make output I equal to nums I minus 1. So what's to the left of it times output I minus 1. Also, we need to fill the output array with 1 because everything times 0 will be 0. So here we'll be multiplying everything to the left of it, including what we've added to the output array, because we want to be able to build the product up rather than just have the number itself. And then here, actually what we'll have to do, okay, so we're going backwards now, and we're going to create a rolling sum variable that equals to 1, or sorry, rolling product. And the reason why this is the case is because what I could do is I could theoretically just create another output array like this, and then add the leftmost, or everything, add the rolling products to the right. However, I don't want to increase the space complexity of this problem when I don't necessarily need to. When I can store everything in a primitive variable like rolling product, it's effectively doing the same thing here, but going the other way around. And the reason why we have to have this variable is because the output array has already been manipulated by the first pass, and now we're going to the second pass. So I'll take output I and I'll multiply it by the rolling product, and then, which is 1 currently, so we're ignoring everything to the right of the rightmost value, and then we'll take the rolling product and multiply it by the current value. And through that, we'll take one pass, store the rightmost product for each relative index, and then here we do, the leftmost product is this pass, and in the second pass we do the rightmost, and we multiply it against its current value by doing this multiplication operator. And then if we just return the output array, we should be good. And we are. Actually, time complexity. So time complexity here is O of n, right there, O of n, so it's O of 2n, which simplifies to n. Arrays.fill is O of n. Space complexity is O of n. Auxiliary. Technically, it's non-auxiliary would be 2n. So yeah. Time is O of n, space is O of n. Okay, so this is just some simple Sudoku validation. Basically, each column, row, and subgrid needs to have no duplicates of its current number. And empty slots are denominated by a period. So we just need to iterate through the entire thing and do the validation. There's no like trick to it or anything like that. But we can speed things up by using hash sets. So if I can do something like this, and then here, this is for the y value. So we iterate through the entire grid, and we're making hash sets for the x and y, which is the columns and the rows. And I can now store the current values doing this. So this will get all the, I actually don't know if these are the columns or the rows. I should probably. So if we iterate, we're going to iterate. This is how it's stored. So we actually do, these technically should be flipped, because this will be, because we iterate through each subarray first. So we'll iterate through the rows first. So if cur x, the current row or current column is not equal to a period, and you cannot add the current x value into the x array, we're going to return false. And then we're going to do the same thing with y. So here, boom. So that takes care of the columns and the rows. Now we need to do the subgrids. So what I'll do is I will iterate through I'll iterate through the board in 3x3 pieces. And then I will iterate through the subgrid. And then here we'll make the hash sets. So if the current value does not equal a period, and you can't add, let's change this actually to like subgrid. Ah, shoot. I like a better one word. You cannot add the current value. We're going to return false. And after all that, we're going to return true, because our validation is done. And I think these need to be characters. Yep. So time complexity is kind of interesting with this, because a Sudoku, the grid will always be a fixed amount. It'll never, like, I guess the board can increase. So I would say we have O of n squared here, we have O of n squared here. We actually have O of n squared in terms of these values. Yeah, so O of n squared, O of n squared. I'm actually going to ask GBT, see if what the time and space complexity of this problem is. Yeah, my guess is O of n squared for both, but it's doing too much. That's what I'm saying. Like, technically, the board shouldn't be any bigger. Oh wait, yeah, you can't make the, I was thinking you can make the Sudoku board bigger, but you actually can't. Yeah. Yeah, that's a hard problem to. I don't remember this one. Oh, okay. So, how we're going to do this is to determine the longest consecutive sequence. What we'll do is we'll store all these values in a hash set initially, and then we'll iterate through each value. And if the value is the lowest, or if the hash set does not contain 1 minus the currently iterated value, we know it's the lowest in its respective sequence. So when we find any of those values, and there can be multiple of them, we're going to continue to see if the hash set has an increment of the current value. And then we'll throw that into a while loop and just keep a counter variable and store the max value in like a max variable that we have. So here we can create a hash set, and we can iterate through all the numbers and add them into the set, and then we're going to iterate through all the numbers, and if set does not contain set does not contain the decrement of the current value, we're going to initialize a counter variable and store the current variable. And if the set contains the current variable, we are going to increment the counter. And then we're going to increment the current value as well. And then we also want something like max, and then we'll store the max value here, and we'll return the max value. And this will tell us the longest consecutive sequence. So let's see. This is O of n. This is O of n. This is also O of this. This is technically O of n because we're at most in this entire block iterating through nums twice, because we're only iterating through unique values with this while. We'll never iterate multiple times with this while. Also, the time complexity should be way better on this. Oh wow, what's up here? It probably doesn't use a set. Oh, that's dumb. That's dumb. That's O of n log n. Okay, cool. That's arrays and hashing. Okay, so what we can do here is we're going to ignore case, and then we're going to check each. We're going to ignore the case on each of these checks, right? So we'll do a 2-pointer here. One on the left, one on the right. So one here and one here. And what we're going to do is we're going to slowly iterate inwards, and we're going to iterate here inwards. And we're going to check each character and see, first of all, if it is a character or not, like if it's not a space or something like that, because we don't care about those, or some sort of punctuation, a type of punctuation. And then we'll also ignore case at the very beginning, and we'll increment in unison from left to right, and we will go slowly close this window in simultaneously from left to right. And as long as there are no unmatching characters, then we are good. So how we do that is we have a left pointer and a right pointer, and we say while left is less than right, and then we'd say if, actually wait, we also have to make s.to lowercase. We have to ignore case. So we're checking if the current left's character is a letter or digit, or is not a letter or digit. If so, we're going to increment, and we're going to do the same with the right. Then, if the pointers do not, so now after all this validation, we know that the left and the right are valid characters, and if they do not equal each other, then we return false. And then last but not least, we're going to increment the left and decrement the right. And then we'll return true if nothing goes wrong. Cool. So space complexity is O of 1, and then time complexity is O of n for the 2-pointer solution. Two sum 2. Okay, so if two sum is sorted, so what we'll do is we'll have a pointer at the left, a pointer at the right, and we'll add those together, and if it's greater than the target, we'll move the right. So we'll make the right smaller, and if it's less than the target, we'll make the left smaller, or left bigger. And by doing this, we can basically do the same thing, close the window down here until we hit target. And I believe, yeah, there will always be one solution. So here we'll go left. Int sum equals numbers left plus numbers right. I need to explain this. So we're making a left pointer, and we're making a right pointer. And while the left is less than the right, we're going to take the sum by saying numbers left plus numbers right. If the sum equals the target, we can return a new array with the indexes. If the sum is less than the target, then we increment the left. If the sum is greater than the target, then we increment the right, or decrement the right. And then we can just return a failsafe, kind of, something like that. There we go. Time complexity is O of n, space complexity is O of 1. I might have a hard time explaining this one. So how we solve this one is, I think the fastest way is to sort this array initially to be able to avoid duplicates. And then we take each value, find the difference between it and 0, or between 0 and it, and then we do the 2-pointer approach that we just did, where with the remainder of the array, where we have, so if we're looking at this first index, we'll take it and say, okay, what pair of values sum up to this complement, which will be 1. So then we take a look at the rest of this, which will be sorted, and then we say, okay, is there anything that adds up to 1? And we go from the left to the right, and we slowly close that window in until we find our target, if we find our target. And then we will add it to a list, and then we'll add those values to a list, and then add that list to the output array if we do that. So here I'm going to sort the nums, and then I'm going to make the output array, and then I'm going to iterate through the array. So if I equals 0 or nums I does not equal nums I minus 1, so if we're at the beginning, or if there are we're not using a duplicate value, because if we have something set up like this in this array above, it won't know the difference between these two if we don't make this duplicate check. So this will, let's say there's a match for -1 later on in the array. This will return the same value as this. So we want to be able to skip this pair if we encounter a duplicate pair or duplicates. So yeah. Next we will take we'll find the complement, which is nums I, or 0 minus nums I, and then we'll take the left, which is I plus 1, and then the right, which is nums.length minus 1, and we'll say while left is less than right, we're doing a two pointer approach. Target, this is our target. So we calculate our complement, and we say nums left plus nums right, which will give us our complement. So if our complement equals the target, we'll make a new list, we'll add nums I, nums left, nums right. So all the different numbers that add up to 0. And then we'll take the output and add the list. Now, after this, we can do some pre-processing to help us a little bit. So while left is less than right and nums.left is equal to nums left plus 1, we can increment left. And the same thing with the right. And this just makes our processing a little faster. While nums right equals nums right minus 1, because we're looking inwards. And then after all of this, we will increment and decrement one more time. And I'm actually not exactly sure why we do this, but I know we do this. Let me think. Okay, so the reason why we do this is because we're checking backwards in both of this relatively. So on the left side, we're checking what's ahead of it. We're checking what's ahead of it on the left side and the right side. So when this condition fails, we know that the current pointer, left or right, is currently at a value that we have already seen and added to the list. So because of that, we need to do this, which is honestly why we do this too. Yeah, so this doesn't necessarily make our processing faster. We need this. I was mistaken. So yeah, that's done. But now we have to handle situations where we are not seeing the complement. So if the complement is less than target, we need to make left plus increment left and then decrement right, and then return the output. I'm going to mess up the time and space complexity of this probably. Yep, so that works. So space n log n is right here. Space complexity. This is O of n technically. O of n here. O of n here. So time is O of n squared. Space is O of n, I believe. That's my guess. And time is n squared, space is n. And then that'll be the last one for tonight. Let's see. Yeah, okay, n squared. That's good. Why is this? Oh, sorting. Oh, wait, but we can drop this value. Because O of k is greater. Yeah, so we're fine. We can actually drop this value. Let me ask you. Can in O k plus log n, can't log n be dropped because it's non-dominant? Respond. You're absolutely correct. Okay, cool. That's all I care about. All right, not too bad, not too bad. We got more work done. So, oh wait, I needed to see how many problems. 14, okay, not bad.